In this video, we are talking about improper integrals, and we're going to go over a really common error that folks make when dealing with them. Okay, so let's look at an example to talk about what this is. Let's say I want to evaluate this integral from negative 2 to 1 of 10 over x to the sixth. So I'm going to first do this in the incorrect way to point out what the mistake is. So I can simplify this function first. This is the same thing as 10x to the negative 6. And now I can do my antiderivative. So I would leave the 10 there because it's just a constant multiplying my function. Then I get x to the negative 5 divided by that negative 5. Now I'm going to plug in those limits of integration, that negative 2 and the 1. And if I simplify this function, it becomes this, negative 2 over x to the 5. If I now plug in these limits of integration, which I've written out here, and I simplify it, we end up with negative 33 over 16. But let's do a reality check on this. I'm going to draw the graph of my function. So on the side, let's draw some axes. Let us draw some axes. And 10 over x to the 6, it has a vertical asymptote at the y-axis. And there's one piece of the function's graph on this side of the y-axis, and then it's symmetric on the other side of the y-axis. So it looks something like this. And my interval that I care about here is from when x is negative 2 up until when x is 1. We know that definite integrals represent the area under a graph. So let's sketch that area. So starting at negative 2, it would be all of this area to the left of that vertical asymptote. And then it also includes this part to the right of the vertical asymptote up until when x is 1. We're finding that whole area. But this whole part of the graph is above the x-axis. So this should be a positive area, but we were getting a negative value here. And that doesn't make sense. So, okay, the area here should be positive, but we're not getting a positive value. So the question now is, well, why didn't this work? Well, this integral, because it has this discontinuity somewhere in the middle, it's an improper integral. It is improper. So as a result, our previous method that we're using here, which is just, we're doing the fundamental theorem of calculus, where I just take the antiderivative and I plug in these limits of integration and then I subtract. That fundamental theorem of calculus doesn't apply. So I will write FTC for fundamental theorem of calculus. This is part 2 technically of that fundamental theorem. It doesn't apply. So the takeaway of this is now, whenever we have an integral, I first need to check if that integral is improper. Because if it is improper, we're going to need to handle it using our methods for improper integral, our techniques that we've learned. Okay, so let's do that. What's the correct way to solve this? We've seen that when our function is discontinuous, somewhere in the middle of our interval, we need to split it. So let's write that down. We need to split it into two pieces. So I'm going to have two integrals. So two integrals here added up. And the first integral will start at negative 2 and then go up until wherever that discontinuity was, which for me is when x is 0. So up until when x is 0. And that next integral will start at 0 and then go up until wherever it should have ended, which is at 1. And then I'll write my function, 10 over x to the 6. Same thing in the second integral. Let's write the function. Okay, so now I've split it up into these two pieces, and I'm going to have to evaluate these pieces. Okay, so let's pick one of them to do first. So maybe I'll evaluate this second one first. So let me highlight it. Let's evaluate this second integral first. So that lower limit of integration is a 0, and that upper one is a 1. Okay, so we've seen that when we have these improper integrals, I got to replace whatever thing is making it improper with a variable. And in this case, my function is discontinuous when I plug 0 in. So I'm going to replace that 0 with a variable like t, and then I keep the other stuff as it is. So there's a 1, and then the function's 10 over x to the 6th dx. And now I'm going to have to take a limit in front. So is it going to be from the right or from the left? Well, if I draw a number line, my interval for this integral is from 0 to 1. And if I'm within the interval and I'm approaching 0, I have to be approaching 0 from the right side. So I'm going to take the limit as t approaches 0, but from the right. Okay. All right, so now let's evaluate this. So I got this limit as t approaches 0 from the right. We already worked out what this antiderivative is up above, so let's just use that. We got that it's negative 2 over x to the 5. I got to plug in the 1 and plug in the t, and then subtract. So I get the limit as t approaches 0 from the right. If I plug 1 into my function, I get negative 2. And then minus, if I plug t in, I'll get another negative. So maybe I'll put a parentheses, negative 2 over t to the 5. Okay, so I can now plug in my limit. So t is approaching 0 from the right. Let's plug that into this part that has a t. Well, this first term is just negative 2. I can just write that. I got a negative 2 in front. And then the double negative becomes a plus. And I get 2 over. So I'm plugging in 0 from the right, like something a little bit bigger than 0, in for the t. So I'm just going to write that symbol, 0 with low plus sign. And then that's being raised to the 5th power. Okay, so I got that negative 2. And then, well, what is this going to be? Well, on my numerator, I have 2. On my denominator, this means I have something very close to 0, but a little bit bigger than 0, a little bit to the right of 0. So imagine something like 0.0001 or something like that. Well, if I raise that to the 5th power, it's also really close to 0, but a little bit bigger than it, a little bit to the right. So the denominator is still going to be, I can still write 0 with low plus sign. And we've seen that if you divide something like 2 by something very small, very close to 0, the whole fraction gets really big, really, really big. So we just need to know, well, is it going to be positive and really big or negative and really big? So the top is positive. The bottom is also positive because it's a little bit on the right of 0. So overall, that's going to make the whole thing go to infinity. So I get negative 2 and then plus infinity, which is infinity. Okay, so at this point, we have worked out this second integral. We got that it's infinity. But that means one of these two pieces diverges because it's not finite. And if that diverges, the original integral also diverges. And that's really nice. I don't even have to work out this other one. So it saves me some time. Okay, so let's write that conclusion. So since one of these integrals diverges, meaning it's not finite, our original integral diverges also. Diverges also. And that's my answer. So if we had worked out this integral and it was finite, then we would have hung on to that value and we would have done the other one. And if the other one was also finite, then we would just have added those two values together to get the answer to the original. If this first one we did had been finite, like if I got a number like 4 or something, and the second one was divergent, then the original one's also divergent. So all it takes is one of these to diverge for the original one to diverge.